Okay, cool. So yeah, thanks for coming, everybody, to this different day and different time. The aim for today is basically to go over everything with regards to first order logic, natural deduction. So in particular, what we're going to do, I'm going to start by just walking you through all of the new rules for FOL natural deduction. The nice thing is there's not that many new rules. The bad thing is some of them are quite complicated. But that's okay. We'll figure it out together. So we'll talk through the rules, then we'll very, very quickly go back over what we're going to call proof theoretic or syntactic concepts. This is basically what we talked about in the recorded lecture last week. Right? These are ideas or kind of parallel concepts to various semantic notions that we defined, in this case, defined in terms of interpretations. And we'll wrap up this section by talking about the interplay between the two. Because again, the big motivation here, what we want to try and get to is a full system where no matter what we're trying to do when it comes to FOL, we can do it. The upshot is effectively going to be certain kinds of activities, we build FOL interpretations. And for other ones, what we would do is construct natural deduction proofs. It's these two together that will give us our full treatment for first order logic. But first, let's figure out how the hell to do FOL natural deduction. So let's talk about the rules here. First thing to say with regards to FOL natural deduction, everything we've done already also plays here. So every one of the TFL rules also applies for when we're doing first order logic natural deduction. We use the same citation system, it's the same names, everything goes through. And that includes both the actual rules and the derived rules. So literally everything that we've done so far, you can also do here. We're going to get a few more rules. Specifically, we're going to get rules with regards to introducing and eliminating our two quantifiers. We're going to get introduction and elimination rules for identity. In fact, identity introduction is probably the weirdest rule that we have. It's extremely simple, but it's fundamentally different than every other rule. And then finally, we'll get what we'll call quantifier conversion rules. These are basically rules that will let us take sentences featuring, say, quantifier next to a negation and change it into a different structure. And the reason for doing that is just simply to make them different structures that we can use. We'll talk about that as we go. So let's go through these one by one. Let's start with probably the easiest, or tied for the easiest, quantifier rule. And this is universal elimination. So the thought behind universal elimination, right, is that if you have something that holds for everything, then it holds for any particular thing. So more generally, if you have a sentence that's got a universal quantifier as the main operator, you can eliminate the quantifier, replacing every instance of the associated variable with any name you want. So if everything's an F, then C is an F. Then D is an F. Then E is an F. Again, if you've got a universal, that means you can fill in the gaps with any name you want. The only thing to note is that you have to replace every instance of the variable. You can't pick and choose. So that's our first one, universal elimination. You take the universal, you replace it, you replace the associated variable with any name you want. No restrictions at all. So that's the first rule, universal elimination. We go from a universal, and then we plug in names. So this rule is fairly easy. Unfortunately, its complement is slightly difficult. Universal introduction is a little more complicated. And the reason is that you need to show, to introduce a universal, that your associated sentence holds for every possible object. It's got to hold for everybody. Now, we could do this with interpretations because we could fix domains, and we could then think about how to fix the extensions to make that work. But we don't have that here. We're just playing around at the syntactic level. So how would we show that it works for everybody? Well, we pull a trick. We can't do this with every possible name. We show that the sentence holds for some arbitrary name. Now, what the arbitrary name is effectively a dummy. It's a name, in name only, that can stand in for any individual at all. Because the arbitrary name is arbitrary, it means that we could have filled in any name, and hence if the sentence holds for the arbitrary name, it holds for every name. It's a little bit easier to see in practice, but this is the underlying idea. So here's how the rule works. If you have a sentence that features a name, and this name doesn't appear in any undischarged assumption, then you can replace the name with a quantified variable, a universally quantified variable. Now, why does this guarantee it's arbitrary? Well, if it's not in any undischarged assumption, then it's just a fucking letter of the alphabet. It's not like it's actually a name for someone. It's effectively a dummy name. If it is in one of our undischarged assumptions, say, one of the assumptions we take right at the beginning, then we're making a claim about that name. And not just making a claim about it, but we're assuming this claim about it. We're taking the claim to be true for the sake of the argument. In that case, that associated name isn't arbitrary. It picks somebody out. In a sense, we don't really care who it picks out, but we know something about that person or that thing, whatever it is, given our assumptions. Now, the thing to note is there's two ways a name could appear in our undischarged assumptions. It could be on the stuff that we assume at the opening of our proof. What's the other way it might be in an undischarged assumption? So it could be right in the stuff that we start at the beginning. Where else do we get assumptions? Yeah, if we're in a subproof. So if we're in a subproof, the sentence that opens the subproof while we're in it, that counts as an undischarged assumption. It will be discharged when we close the subproof and step back into the main proof line. But while we're in the subproof, any name that's on that opening sentence, that is in an undischarged assumption for the duration of the subproof. So that means if you start a subproof, say with a sentence featuring C, you can't get rid of it using the universal while you're in the subproof. So again, elimination, to go back, very easy. Elimination is if you have a universal, you can replace the associated variable with any name you want. Introduction, if you have an arbitrary name, then you can replace it with a universally quantified variable. The big restriction, to make sure that it's arbitrary, the name can't appear in any undischarged assumption, any assumption that we're holding on to, at least at the moment that we're doing the introduction. There's also this restriction, that the variable we're going to introduce can't already be in the sentence. That's not a terribly exciting restriction because that's basically just saying don't have the clash of variables. If the variable's already there, you can't introduce a new quantifier attached to the same one. The big rule is this. And this is going to come up again when we talk about existential elimination, this concept of using an arbitrary name. But again, the thought is when we're doing or using arbitrary names, it's some kind of dummy name that stands in for any object you want. Grammatically, it's a name, but really, it's just a kind of space filler. Okay. Now, before we go anywhere else, questions on universal introduction and elimination. So? Okay. Let's rock along. The other very easy, please. Yes. So, it's an assumption that we're taking to be true. Now, this could be, and importantly, it's an assumption we're taking to be true that we haven't decommitted from. So, it could be one of the sentences we start with that's above our assumption line, which we're never going to discharge for the duration of our whole proof. Or it could be the sentence that opens our subproof. Until we close the subproof line and step back into the main proof line, the sentence that opens it, the one that we draw our little sub-premise or sub-proof assumption line on, that counts as another undischarged assumption. We're taking it to be true, at least until the end of the subproof, and then at the end of the subproof, when we close it and move back a line, we have discharged it. So it's either some of the sentences we start with above the assumption line, or the first sentence in your subproof. Good. Okay. Make sense so far? Please.
So names that refer to object can be A, B, C, or replace all.
Sorry, I couldn't hear you.
If we have, so here we have like CCC, that refer can be A, B, C, D.
Could be, but note in that case, if you wanted to get rid of all of them, you would need to replace each one in turn. You can't replace different names with a single kind of quantifier. So if we had a sentence that featured A, B, and C, and all three of them were arbitrary names, you could introduce three universal quantifiers. One for A, one for B, one for C. You couldn't do one that wipes all of them out. It's always replacing every occurrence of the one name. Okay, cool. So that's the universal. The existential, thank God, is very easy. The existential is, if you have a sentence featuring a name, you can replace some or all of the occurrences of the name with an existentially quantified variable. So if you have, for example, LAA, you can introduce an existential to give you there is an X such that LXA, replacing the first occurrence. Or you could replace the second and get there is an X such that LAX. Or you could replace both and get existential X LXX. All of these are equally good moves. Because the thought here is, well, remember, the existential is just there's at least one. So if you know it holds for some name, then you know it holds for at least one thing, whatever name that was. So the really neat thing is, for example, if you have TCC, you could apply existential introduction twice. Once to give you, say, this sentence, and then once more to give you there's a Y and there's an X such that TYX. The only restriction is that the variable you use can't already be in the sentence. And again, that's just to make sure that we don't have a clash of variables. This is a very, very lovely and easy rule. It's almost as easy, if not just as easy, as universal elimination. So universal elimination's easy. Existential introduction's easy. Universal introduction is quite hard. existential elimination is the hardest. The reason that existential elimination is the most difficult is that existentials are basically disjunctions. An existential is effectively equivalent to, right, for A, or for B, or for C, or for D, or for E, for every single possible name. And just like how disjunctive elimination was difficult, same issue is going to happen here. The nice thing is we can make do with arbitrary names to help us out. So here's the idea. This is what we're going to encode into our rule. If you have an existential, we will replace the related variables with an arbitrary name. We'll then do some reasoning about the sentence featuring that arbitrary name. And finally, in the end, we'll get rid of the arbitrary name to get some result that will hold no matter what name we used. So here's how it looks. Forgot. We'll give you an example to show you. Suppose that we know, or we're going to assume, something is F, and everything that is F is G. Should already be pretty clear. One of those is going to be an existential, one of those is a universal. Suppose we wanted to conclude that from these two, something is G. That has to be true, right? Something is F, everything that's F is G, so whatever it is that's an F must also be a G. So how do we show that? Well, we start by, we don't know what object it is that is an F, but we can name it. We'll just call it Steve. Who is Steve? We don't know, we don't care. Steve is a name to help us grammatically talk about the thing that is F. And in fact, even calling it the thing that is F is slightly wrong. Steve might be a name that picks out a ton of things, because something is F might be everything is F. So we just introduced the name Steve as a shorthand for an F thing. So we introduce this arbitrary name Steve, and by stipulation, we know Steve is F. It's just part of who he is, or what he is. We then know, since everything that is F is G, Steve must be G. Finally, we get rid of the use of Steve, because that was just a way for us to talk, and we can go back to an existential and say, cool, so something is G. Who? I don't know. I was calling him Steve, but I don't really know who that is. What's really important here is that nothing in this reasoning depends on knowing what Steve is. Steve is just a grammatical element here introduced for us to do our reasoning. Steve is an arbitrary name, and because it's arbitrary, this reasoning remains completely general. I could replace Steve with Alice, and the whole thing would go through. So before we go on, does everybody kind of get the grip on the reasoning here? And if not, that's okay, right? It's weird. The reason why we have to do it, maybe this is helpful, is what we're always doing is we're stuck just thinking at the grammatical level, at the syntactical level. And since we're stuck at the level of syntax, we have to make use of these kinds of dummy names, because otherwise we wouldn't really have sentences. We would just have is an F. And that's not really something we can work with. So we have to plug in some name. But we don't want it to be the name for some object, some particular thing. This is why we have to have an arbitrary name. So here's how we encode it in the rules. You have an existential. You then open a subproof where you've replaced the associated variables with an arbitrary name. That is, it's a name that isn't already in the sentence, and it doesn't appear in any undischarged assumptions. So this guarantees the name we're using is genuinely arbitrary. You then do some reasoning inside the subproof. And whatever sentence you get at the end of the subproof cannot feature the name that you used. So the reason is, if it features the name you used, the name no longer becomes arbitrary. It matters that we used Steve rather than Alice, rather than Bill, rather than Fred. To go back, right, the broad reasoning here. We didn't end up with a sentence featuring the name Steve. We ended up with a sentence where that's gone. So generally, the idea is that ensuring the name is a dummy, the name can't appear in any undischarged assumption. It can't already be in the sentence that we're going to play around with, the existential. And it needs to be gone by the end. Because if it's not gone by the end, then we're talking about that particular name. It is no longer an arbitrary or dummy name. So again, the three restrictions here. Not in any undischarged assumption, not in the sentence already, and it's got to be gone by the end of the subproof. And what we can then do, you get to that sentence that does not feature your arbitrary name, and we can derive it one line to the left of the subproof we started with. This is the most complicated rule that we're going to get with FOL. All of the complications are driven by the grammar of our language and the fact that we have to use arbitrary names here. But if you know these three restrictions, you're going to be fine. Otherwise, it's basically disjunction elimination. Okay. And before we go on, pause. What questions do you have for me on this one? Be honest, it's okay. This is weird. This is the hardest one by far. Importantly, well, not importantly, but a pro tip here. Weirdly, a lot of times, the last rule you will use in these kinds of subproofs is going to be existential introduction. That seems really strange. But the reason the last move in the subproof is going to be existential introduction is it's an easy way to guarantee that you get rid of the arbitrary name. You get rid of it by replacing it with an existentially quantified variable. In fact, that's exactly what we did here. Right? We had the name Steve, and then the last move in our subproof is to get rid of Steve by existential introduction. Not always, but this is frequently going to be something you can do. Get to the end where you've reasoned using some particular name, get rid of the name by existential introduction. The next rule I'm going to talk to you about is probably the other way. Well, not the next one. 2 rules from now is the other one that you'll use. Okay. So far, so good? I should also stress, if it's not clear yet, that's okay. These are, much like the other rules, stuff that will become clearer as we go through some sample problems. As you kind of apply it a few times and start to see how it works. Okay. So here's just a kind of natural deduction version of that reasoning I gave you 2 slides ago. We had something as F, we had everything that's F is G. What did we do with Steve? Well, we just jumped into a subproof where A here is our arbitrary name. We did universal elimination, then conditional elimination to get GA, and then existential introduction to get rid of A, to give us a sentence that does not feature the arbitrary name we've used. Then we can stake that out back into the main proof line through existential elimination, citing the existential, and the subproof where we use the arbitrary name. Just a kind of case. Okay. The last kind of rules or collection of rules, but please.
Yes, this one. I understand why we have the arbitrary name, and then in line 6, we're not using it.
Good. So importantly, we want to use the arbitrary name because we want to talk about the thing that's F. So this is where we introduce the A, right? Steve. But to make sure that the reasoning we have doesn't depend on using that name, we have to get rid of the name by the end. Because otherwise, it would hinge on the fact that we used A in this case, or Steve in the English case, right? Because if we got out, Steve's a G, the response is, who the fuck is Steve? Because that's just an arbitrary name. It shouldn't be some specific one that we've used. So if the result features a specific name, then the whole rationale was actually about that name, not some arbitrary one.
If we have a subgroup of the subgroup, can we use the same arbitrary name?
No, because if we're in a sub-proof, right? So imagine, right, we've got a subproof that started with us using A as an arbitrary name. We couldn't use A again in our sub-subproof because A appears in an undischarged assumption at that point, namely the assumption we opened our first subproof with. So that's why we would be prevented. It's not arbitrary at this point in the reasoning. So that's the kind of block there. Okay. Yeah, there was a second question.
Yeah, for the next.
Absolutely.
Why do you not have to mention sentence 3 and sentence 4? Because you say the FA.
Good. So importantly, right, sentence 3 is our kind of arbitrary, it's our introducing the arbitrary name. So in this case, it can count as our undischarged assumption for the sake of the subproof. And that's why it's opening, right? Just like every time when we open a subproof, that additional assumption, we don't need a rule for it. We just assume it, but we got to get rid of it by the end. And then line 4, in this case, is simply produced by eliminating the universal at line 2. So remember, line 2 is a sentence featuring a universal quantifier as its main operator. The rule there is you can replace the associated variable with any name you want. So in this case, we did it with A to give us the conditional. And the reason is, given that opening assumption at line 3, if we use A in the universal elimination, we can then get GA. So that's the kind of rationale here. Good. Yes?
Yes. When it comes to proofs, it's very useful for me to kind of paraphrase it.
Mm-hmm.
Not paraphrase it, but I look at something like this, and I remember your example that you say when it comes to contradiction, if A is not true, then bad things happen.
Yeah.
Could you maybe try to do it this one?
Yeah. So importantly, this is kind of what we were trying to do with the Steve case, right? Is that, look, if it holds for Steve, it'll hold for anybody. Because who is Steve? He's just anybody. That's really what we're after whenever we use an arbitrary name. Note that that same reasoning is going to work here just as much as it does here. It doesn't matter that we were talking about Steve. We could have been talking about Alice or Bill or Teddy. The name is irrelevant. It holds for everyone. In this case, it doesn't matter that we used Steve. We could have used Alice or Bill or Susie or whoever. The reasoning would go through just the same. That's the kind of intuitive idea. It's very hard to compress that down into a little witty aphorism, just because the different ways that subproof can go. But the broad idea is that you want to ensure whatever result you're getting here doesn't hinge on the fact that you use this name rather than that one. If you do that, we've screwed up. It's not arbitrary that we used Steve rather than Alice. That's the key truth. Okay. Okay, so far? I very much appreciate this is weird. It is. It's something that as we do some exercises, it's going to be more familiar, but it's useful to see. So, the next collection of rules are actually really easy. So I'm going to give them to you all at once. These are the quantifier conversion, or CQ rules. Conversion of quantifier rules. These just tell us if you have a sentence with a quantifier next to a negation, whichever way it is, you can flip them to the other setup as long as you flip which quantifier you have. So if you have a universal negation, you can apply CQ to give you a negated existential. And that's vice versa as well. And similarly, if you have, let's see, an existential negation, you can switch them around and get a negated universal. Again, generally, the rule is if you have a quantifier next to a negation, you can change places. You just have to flip which quantifier you have. And it goes from one way or the other. It doesn't matter. These are going to be very useful depending on what you're trying to do. A lot of times they're extremely helpful because say you have, let's go up there, the negated existential. That's really, really hard to use because the main operator there is the negation. So you use CQ to give you a sentence that's really easy to use, a sentence featuring the universal. Because you eliminate the universal, and then you have a sentence with a negation as its main operator, but it can feature any name you want. So that can be very handy. Similarly, if you're, say, trying to generate a contradiction, having a negated existential can be extremely helpful because getting an existential is really easy. If you have a sentence featuring a name, cool, get rid of the name, insert the existential. So these are situational rules. They're helpful every once in a while, mostly for just getting whatever you want to the front so you can then manipulate the sentence. Okay. The last two rules have to do with identity. So first, we have identity introduction. Identity introduction is whenever you want, you can introduce an identity claim with the same name on both sides. But it has to have the same name on both sides. So you can introduce A equals A, you can introduce E equals E, you can introduce, C equals C, whatever you want. This is the weirdest rule in some ways because it is the only rule where we don't cite anything. It is literally giving you a sentence from nothing. But it's a derived sentence. What's it derived from? Nothing. So the thought behind it is because of the way we've set our system up, every name must name something, and every name has to name the same thing as itself. So we get this effectively for free, but we want to have some way to make it clear that we're introducing this line, that it's not a further assumption. So this is why we have this rule. So identity introduction, you can introduce an identity statement with the same name on both sides. Identity elimination is substitution. If you have an identity with two names on either side, then any sentence featuring one name, you can replace with a sentence featuring the other name. Note you can do some or all of the occurrences. So if you have like FAA, you can use identity replacement to get FAB or to get FBB. Again, It's just substitution. If you know that two names pick out the same object, then everything true of one will also be true of the other. So identity elimination gives you really boring identity claims, same name on both sides. Identity elimination lets you substitute if you already have an identity.
So how we can get A equals B if we can apply the equals I always the same.
Nice. So one of the ways we might get it, let's think about, remember when we talked about the. So we said the F. That sentence has two clauses in it. It says there's at least one F and there's at most one F. So think about the at most one F clause. It has an identity statement as the consequent. Everything that's Y, or everything that's an F, is going to be equal to my X. Cool, okay. So if we could get the antecedent there, we can get the identity statement with different names. That's one way. Sometimes it will also just be given to you as an additional assumption. But you're right in that at least from these, without the right kinds of assumptions to feed in, you're never going to get A equals B. But that's good. You need to show that they're identical rather than just assuming. Okay, cool. That's it. Those are the rules. Existential introduction, universal elimination are both very easy. Universal introduction, you have to have an arbitrary name that you can then replace. Existential elimination, you have to use an arbitrary name in a subproof, get rid of it, and then get some result. The quantifier conversions, again, quantifier next to a negation, you can swap places as long as you swap the quantifier. Identity elimination gives you a very boring identity statement. Identity elimination lets you substitute. And then, of course, all of the stuff that we've done before. The key thing is that rules only apply to the operators that are the main operator. So if you have a sentence with a quantifier in the antecedent, you can't eliminate the quantifier. You have to go through a conditional first. Elimination rules only ever apply to main operators. Introduction rules only ever give you main operators. This is very important because there'll be some times when it's really clear what we need to do, but there'll be a bunch of quantifiers in the way. So we got to go through them, do what we need to do, and then add them back. Okay. Cool. How are we doing? Perfect. So that's all the rules for FOL. And just like with TFL, we're going to be able to do the same kinds of things that we did before. So we're going to have the exact same concepts. We're going to have the notion of a theorem. Right? A theorem is going to be a sentence that can be proved from no assumptions whatsoever. Now, if you remember with TFL, for natural deduction TFL, the first move you will always make in proving a theorem for TFL is opening a subproof. 99% of the time when doing it for FOL, same. There's one exception. There's one exception. What would the exception look like? I gave you a rule that lets us get a sentence from nothing. Yeah. Identity introduction. Identity introduction is the one exception. So 99% of the time when you're proving theorems for FOL, your opening move will be something involving opening a subproof. The 1% exception is when you do identity introduction to give you A equals A at the beginning. Those will be very rare.
Because you don't need it.
Because you don't need any lines, right? Again, it just gives you the name. It gives you the identity statement with the same name on either side. So it gives you a sentence from nothing at all. Yeah.
But isn't it still an assumption?
So it doesn't have to be, right? The nice thing is that this is a rule to derive a sentence. So we could just introduce A equals A at any point in any proof. We don't need to cite anything because its truth isn't backed up by some assumption and applying an inference rule. It's backed up by the way we've set up our FOL system. Yeah.
In what scenario would that actually be useful to say like A to B?
So if we wanted to show that, for example, some x is identical to some y, that is a theorem. Start with identity introduction, existential introduction, jump done. You could also do every x is identical to every y, which is weird. But we couldn't quite, well, we'll talk about that. This is something we'll come back to. Sorry?
We do it in programming.
Yeah, it's the same kind of idea, right? Identities can bootstrap. So there's proving a theorem. There's also going to be the notion of provable equivalence, right? Just like with TFL, A and B are provably equivalent if you can assume A and derive B, and then assume B and derive A. You got to give both proofs to show that it's provable equivalent both ways. Same stuff as with TFL. We also have the notion of joint contrariness, right? Some sentences are going to be jointly contrary if and only if you can take them as assumptions and derive a contradiction from them, just like with TFL. Now here's something interesting. Suppose we wanted to show that an FOL sentence is not a theorem. How would we show an FOL sentence is not a theorem? Well, the fact that we could derive it using an assumption doesn't mean, or doesn't show, obviously, that it's impossible to derive it without any assumptions. So how would we show that it's impossible to derive it without any assumptions? Well, no. So right, just take A equals A is a theorem. But A equals A is also something we can introduce at any point in any theorem. So that doesn't mean it's not a theorem anymore. Again, let's just take a whole slew of assumptions. Let's go back. In our toy proof, I could, before doing the conclusion, just introduce A equals A using identity introduction. It doesn't mean that A equals A isn't a theorem. The fact that there is some possible theorem or some possible proof that starts with some assumptions and gives us our sentence doesn't show me that there isn't also a possible one starting from no assumptions at all. So, how do we show that a sentence isn't a theorem? Well, here's the trick. We can't do it with natural deduction. What would we do? We couldn't, this is FOL. So what would we do to show that a sentence is not a theorem? We can't do it with natural deduction. Well, let's think. What semantic concept is theoremhood very similar to? No, tell me. Yeah, so that's the notion for TFL. What was the parallel notion? So it's not tautology for FOL. Does anybody remember the semantic concept for FOL? Yeah, so that's the big broad concept. It's a little narrower. Logical truth, right? So tautologies are sentences, are TFL sentences true in every valuation. Logical truths are FOL sentences true in every interpretation. Here's the cool thing. If we've set this up right, every logical truth should be a theorem. Every theorem should be a logical truth. So if we can show that a sentence is not a logical truth, we will have indirectly shown it is not a theorem either. Similarly, how would we show that two sentences are not provably equivalent? We give an interpretation that makes one of them true and one of them false. Because we couldn't do this using our natural deduction system. Here's another one. How would we show that an argument is invalid using our natural deduction system? Unfortunately, we can't. We could just keep going infinitely trying to make the proof work. To show that the argument's invalid, we do what we did in the midterm. We build an interpretation that makes the premises true and the conclusion false. The upshot is that there's going to be a tight relationship between these proof theoretic and semantic concepts. And we can exploit that tight relationship to give us the full system. Remember, we talked about introducing the single turnstile, which represents provability. And we have the double turnstile, which represents entailment. And depending on which language we're thinking about, it could be tautological entailment, if it's TFL, or it could be logical entailment, if it's FOL. Similarly, for our single turnstile, there's TFL natural deduction, and there's FOL natural deduction, provability. These are different notions, but they line up perfectly. The provability will hold if and only if the semantic entailment relation also holds. So this gives us this tight relationship. An argument's going to be valid if and only if the conclusion can be proven by assuming the premises. Two sentences are logically equivalent if and only if they're provably equivalent. This also means if we show that one side fails, then the other does too. Sentences are jointly consistent if and only if they're not jointly contrary, and vice versa. So if you can take them as assumptions and derive a contradiction, you will have shown that they're jointly inconsistent. And remember the stuff we couldn't do with interpretations. We couldn't show that some sentences were jointly inconsistent. Now we can. We show that they're jointly contrary. We couldn't show that an argument was valid. Now we can. We build a proof. We couldn't show that two sentences were logically equivalent. Now we can. We give you two proofs to show that they're provably equivalent. There's the Death Star. If we want to show that a sentence is a logical truth, cool. We prove it's a theorem. If we want to show it's not, cool. We build an interpretation. If we want to show a sentence is a contradiction, we can prove it. How do we prove it? We take it as our one assumption and we derive a contradiction. If we want to show it's not, we build an interpretation. So going way back to the end of week 6, if you remember, I gave you something very like this, but it had gaps here, here, and there's. Now we have the machinery to fill it in. Yeah.
So in the end, contradiction is just draw the contradiction.
So it's not going to be one step, because sometimes to show that a sentence is a contradiction, you'll have to pull it apart and get a sentence and its negation. But that will show that the sentence by itself leads to bad things. So this is the kind of really cool thing. Everything that we've been doing builds up to this. So now, in theory, and I want to stress, I'm not going to actually ask you to do this, but note, in theory, you could get an FOL argument, and you could show that if it's valid, why it is, by building a proof. And you can show if it's invalid, why it is, by building a counter model, an interpretation that makes the premises true and the conclusion false. So given you all of the tools you would ever need to do this now with TFL or with FOL, at least in principle. Of course, we're going to work on the skills for building these FOL proofs, but this is the big upshot, which is so fucking cool. It is worth noting, everything I've said there hinges on the idea that the single and double turnstiles perfectly match up. And I haven't proven that to you. I haven't shown that to you. You just have to take it on faith. And in fact, proving that is a pretty significant endeavor. So this is proving the soundness and completeness of our systems relative to each other. If you're interested in this, we do have a little textbook, a supplementary textbook, that goes through the soundness and completeness proofs for TFL. So this is it's a little book called Logic. For those of you who are interested, it's in the files folder on Canvas. Feel free to read it if you like. It goes through some stuff that just, frankly, we don't have the time or the space to be able to talk through. It's very interesting if you're interested at all. And if you're really keen to see how the FOL stuff works, email me, I can send you some stuff. But it is very difficult to prove. Yes?
Is the book like you have like Michael Cohen says, like this attention economy, like like meaning like is it like pure facts under each other?
No. It's got some explanations as well.
Yeah.
It's worth going through, but it's tough. It's tough. But it's still very interesting and worth thinking about. But for our purposes, what's really useful? Again, what I'm going to ask you about, what I'm going to test you on, I want you to be able to build natural deduction proofs. So I'm not going to ask you to build any interpretations. So note that that is now a skill you have. It is going to be, here's the thing, give me an FOL proof. We'll talk more next week and the week after about the nature of the final exam. But this is all the stuff I'm going to examine you on. Next week, it's technically labeled as Natural Deduction for FOL Part 2, but I don't really have more about this to tell you. I could add some more stuff, but frankly, I'm not sure it would be terribly useful. I think this is hard enough already. So what we're going to do next week, it is an entirely supplementary lecture. I'm going to show up and I'm going to talk to you about some extra interesting things. Specifically, we'll talk about some alternative ways to think about logic, some different logical systems. And we'll talk a little bit about a notion called expressibility. In particular, I want to think back about how many operators do we really need to be able to get our truth functional logic system. So we'll talk a little bit about it. It is entirely for fun. There won't be any questions on the exam about it. So please come around if you have the time, but I'm not going to feel bad if you don't. Though I know somebody who will, because there's also going to be an announcement about some society stuff, so do come along for that. But in the tutorials this week, what we're going to do, we're going to start our first exercises into FOL natural deduction. Have a look over some of them, see if you can kind of get a feel for it. But don't stress if you haven't, because what we will be doing in this week's tutorial and next week's tutorial is FOL natural deduction. Right? So we're going to talk about some stuff in the lecture, but we're going to just be doing this stuff in the tutorials. Cool? Thanks for coming at the weird time, guys. Have a lovely, lovely time, and we'll see some of you for the rest of the week.